Now, B part 5, Lie derivative and Killing vectors. Lecture 1, geometric idea behind the Lie derivative. It measures how a tensor field changes along the flow generated by a vector field. In essence, it captures how a geometric object is dragged along the flow of a vector field and compares its value before and after. You see this clearly when we derive from classical mechanics the Lie derivative. Now, the derivative is formulated entirely within the framework, attention now, of the intrinsic geometry. You see? Intrinsic geometry. And the tools for the intrinsic geometry is the exterior algebra. You see, you see this ahead, okay? In the later on the other parts. So, in other words, it does not require any extrinsic reference, okay, to an empirical space, coordinate system, or even a metric. You see, so the Lie derivative is closely related to the intrinsic geometry, manifolds, and so on. Now, the Lie derivative plays an important and conceptually powerful role in both classical mechanics and electromagnetism. In classical mechanics, with the object of this lecture is this, particularly in the Lagrangian and Hamiltonian formulations, the Lie derivative is deeply connected to the symmetry you already saw in part 4, okay? In this case, Villanovan's theorem, conservation laws, and the flow of dynamic system in the phase space. You see, phase space is related to the Hamiltonian, okay? Is the momentum and, in this case, the coordinates and momentum. Lagrangian is related to the coordinates and velocities, as we pointed out in previous videos. So that's the idea, okay, of the Lie derivative. Next, we'll derive in detail, okay, the Lie derivative, okay, and after the killing vectors, okay. That's a little introduction to geometric idea behind the Lie derivative. See?